Hello friends, good morning. Welcome back to our channel ALP Talks. This is your Lakshmipathi. So today we are going to discuss this topic of seminar on variable frequency drives. So let's discuss it. So what is the importance of variable frequency drives? Where we will use it? So why we need it? So whatever you are watching here, that is the motor and we have pump setup here. All these variable frequency drives mostly we will use in all the process industries where we need some torque and rotation and all. In those cases, we have a lot of advantage with the variable frequency than normal direct starter. So it will provide a lot of flexibility in the operation. It will provide energy savings also, and simultaneously it will help the system to be healthy, electrical system to be healthy and safe manner. And the asset, whatever motor or whatever it is there, it will also ensure for a good performance and all. Yeah, so let's go into the details so that you can get better understanding what it is and other topics also you can get it. So in today's the contents are introduction to variable frequency drives, working and illustration, why we need a variable frequency drives, and testing of variable frequency drives, switching frequency testing, application of variable frequency drives, types of drives based on tracing and application. So this is the variable frequency drive, whatever you're watching here. So we have AC line, we have input rectifier, we have inverter. That's what we will use for inverting DC to AC, and we have DC bus here. So this is the variable frequency drive setup. Simply, it will be like this. So at the input side, we can use any normal rectifier. There is no issue on that. But at the output side, we should use a good and advanced inverter technology so that proper signals and supply can be fed to the motor. Yeah. So let's go to the more details. So the working principle, the voltage on an AC, the AC power supply rises and falls in a sinusoidal pattern. When the voltage is positive, current flows in one direction, and if it is negative, the current will flow in opposite direction. So the VFD type of power system enables large amount of energy to be efficiently transmitted over greater distances. The, the rectifier in a VFD is used to convert incoming AC power into the DC power. One rectifier will allow power to pass through only when the voltage is positive, another the vice versa. So this is the sine wave we can see. So 0 to 360 degree. The positive cycle is the 0 to 180 and the negative cycle is from 180 to 360 degrees. This is the input waveform. We will say AC sine wave. Say we consider the magnitude as 1 unit. So this is the pulse width modulation signal. Say this is the sinusoidal signal. So let's discuss a few more things. On time voltage output. Here you can see this is the voltage output and off time frequency output. Here you can see it is sometimes it is off. So that we will say frequency output. And we have switch frequency, corner frequency in hertz. So these things we will discuss in the coming slides also. Yeah, here normally two rectifiers are required for each phase of power. In practical case, rectifier makes use of SCR along with parallelly connected freewheeling diodes in order to get continuous pulses in the same direction. So here you can see three-phase supply is there. We are giving to the network. You have inductor and current is there. So current source inverter and then we fed to the motor. So we need some rectifier gating circuit also for this the entire setup. So we are using some current error amplifier and actual current data we are getting as a sensing element, and based on that we are giving firing circuit to the rectifier circuit. So let's go into more details. Since the more large power supplies are three phase, there will be minimum of 6 thyristors, hence the term we will say 6 pulse rectifier is used. SCR also have gate circuit that enables a microprocessor to control when the power may begin to flow, making this type used for solid state starters. After the power flows on the rectifier, it is stored on the DC bus. The capacitor accepts power from rectifier and stores it, and it delivers to the inverter section. The DC bus also contains inductors like inductors, DC links, chokes, etc. And it smooths the incoming power supply to the DC bus. The final section of VFD, the inverter section delivers power to the motor. The common choice in a VFD is IGBT. We will say insulated gate bipolar junction transistor. The IGBT uses PWM technique for simulating a sinusoidal current wave at a desired frequency. So, inverter circuit generates an alternating current by sequentially switching a DC in alternate directions through the load. So, whatever you are watching here, let's see. For example, we will get all these set up in the module format if you want to build the hardware. So, one output module. This is one complete output module. So we will similarly, we will say second output module, third output module. So in this case, we have 3 output modules. So we will say A, B, C. Each leg we will say A, B, C. And the top portion we are calling as 1 and bottom portion we are calling as a 2. Here we have transistors. So the black color, whatever it is there, that will indicate the direction of flow of conventional current. So we have freewheeling diodes across this transistor. So we have, say for example, the red color is for indicating one direction of power flow, and the green colored arrows will indicate the opposite direction of power flow. And you can see here, this is the voltage pulses, and whatever sinusoidal it is there, that is the current waveform. So let's see more details. Inverter circuit generates an alternating current by sequentially switching a DC in alternate directions through the load. That's what I'm repeating again. So whatever the circuit is there, it is simply DC. It will use it for keep on turning on, turning off, turning on, turning off, like that. So this is the motor. You can see it here. So from the mid of output module, we taken the connections and we given back to the motor. The motor in this case here, it is delta connected. So in this way, there is a keep on looping will be there. DC to again positive, DC to positive to negative bias, negative to negative, the supply will keep on flow like this. Similarly in other case also. Yeah, so let's come to the more details here. The red color shows the single positive pulse and the green shows 180 electrical degree. The freewheeling diode protect IGBT from reverse bias. The red color shows single positive pulse and green shows 180 electrical degree. The freewheeling diode protect the IGBT from reverse bias inductive surges due to motor field decay, which results in transistor turn off. So, to analyze, assume a conventional current flow from positive to negative direction. The black arrow on the emitter indicate the direction of conventional current through the transistors. This is a 3-phase drive, so at certain times during the cycle, transistor will be turned on to cause current flow through AC and BC motor windings. For more clarity, now assume that freewheeling diode are non-conducting and transistors 1A and 1B are turned on and off by the microprocessor control, and the current flows from DC positive bus through the motor windings as shown by red arrows, producing positive voltage pulse and back to the DC bus negative. This is what I'm just explaining here, the red flow. Similarly, to generate next half cycle, transistors 1B and 2A are turned on and off, and the current flow will reverse through the motor winding shown by green arrows. whatever the green arrows are there, that will indicate the current flow. So let's go to the further details. Illustration of the switching sequence. Switches closer to the positive bus are shown in red. Switches closer to the negative bus are shown in black. Open switches are shown in gray. When a particular winding is connected to the same bus potential, the voltage across the winding will be zero. If a winding is connected, so that the positive voltage is connected to the first letter of the winding label. That example, A in AB, BC, B in BC, C in CA, something like that. If a winding is connected so that the positive voltage is connected to the second letter of the winding label, the current flow reverses and the voltage produced across the winding is of negative polarity. So the following one shows the list of number of electrical degrees through which the switch operates and the resultant phase voltage produced. On a 6-pole, 6-step drive, the output devices will be closed throughout the listed operating range. The PWM drive pulses will be produced through this range. You can see here, this is the case one. So this for the first 60 here you can see 60 degree, 120, 180 degree, 240, 300, 360. We kept like different sequences. So here the waveforms are already available. So first, for example, all the red color ones are shown for the positive bus and black color ones are shown for this negative and gray color is open. So what happens? This is the normal circuit actually. So this is the case one arrangement, how it will operate. In the case two, you can see that there is some little bit different. So here, these two switches were turned on. Whatever bottom switches are there, those two were switched on. So it will conduct from 60 to 120 degree. So the path will be like this. So whatever the flow will be like this. In similar way, let's go to the third case. Here you can see similar. It is 120 to 180 degree. Here we opened bottom one and we given supply to the triggering to the 3A. So in similarly you can see in the case 5 here you can see 1B 1 to 2A and this 2 one B. This all the A, B, C. We are naming it like that. So whatever bottom we have, that we will say second one. So here second A and here first B. We just given the supply and it is conducting for 240 and 300 degree. So similarly, we have another here. This is again another circuit. Here you can see whatever 2A we have and simultaneously that 2C is getting conducting and B also 1B is also getting conducting. At a time, if you see any three thyristors or three switches will be in on position so that power flow will takes place from DC bus to the induction motor in a different manner. Yeah. So let's go to the different thesis. So this is the pulse width modulation sine wave synthesis. So low frequency is there. Whatever the width is there, we will say pulse width. This is a complete one cycle and resultant sine waveform with the current. We will say that the magnitude will be like a DC link voltage magnitude, and if it is a high frequency, larger pulse width produce a higher resultant voltage. That's true. If frequency is high means it will take more time to complete a cycle. Yeah. So here let's go to the next. You have PWM drive characteristics. So variable frequency drive DC link voltage is constant. Pulse amplitude is constant over entire frequency range and equal to the DC link voltage. That we have to remember here. Lower resultant voltage is created by more and narrower pulses. Higher resultant voltage is created by fewer and wider pulses. Alternating current output is created by reversing the polarity of the voltage pulses. Even though the voltage consists of series of square wave pulses, the motor current will closely approximate a sine wave. The inductance of motor acts to filter the pulses into the smooth AC current waveform. Yeah, so voltage and frequency ratio remains constant from 0 to 60 Hz. For example, for a 460 volt motor, this ratio is 7.6 volts per Hz. To calculate this ratio, we will simply divide the motor voltage by 60. At low frequencies, the voltage will be low and vice versa. So why we need this variable frequency diode? Now, whatever we discussed till now, this is about the operation, how the circuit will be, how we are doing. Now, why VFD? VFDs provide most energy efficient means of capacity control. VFDs have lowest starting current of any starter type. VFDs reduce thermal and mechanical stress on the motor and belt. This is one of the most important thing we have to keep in mind. VFD installation is as simple as connecting the power supply to the VFD. VFDs with the AFE advanced fiber optic engineering can meet even the most stringent harmonic standards and reduce backup generator sizing also. And VFDs provide high power factor, eliminating the need of external power factor correction capacitors. So VFDs provide a lower kVA, eliminates sags and power outages. So how we can test this VFD? The VFD drives are generally sensitive to ambient conditions, minus 15 to generally 50 degrees centigrade, and in storage and the transport up to 70 degree we can go, and lower side minus 40 we can go. Also, IEC ratings also we have to check it. However, the commonly done tests are forward reverse bias testing and switch frequency testing. These are the some tests we will do on these VFDs. So, what are the tests we will do? Let's here forward reverse bias testing rectifier section. So the rectifier section, keep the positive probe of the multimeter on U plus U of the DC section and the negative over the phases R by B. Then you can obtain some of the results here. R by B. Positive probe of multimeter 0.3 volts, 0.3 volts, 0.3 volts. In reverse bias, it is OL. For reverse bias, put the negative probe of the multimeter on the plus U of the DC section. The above table gives value for reverse bias also. So, and one more thing, keep the positive probe of multimeter on U of the DC section and the negative over the phases of RYB. Then you will get this similar voltages 0.278, 278, 278 like that. So, above table gives values for reverse bias also. And then we have inverter section. Similarly, for inverter section also we will do like rectifier section. So we have now switch frequency test. Switching frequency test, what we will do actually. There are some 3 kilohertz, 2.25 kilohertz and 5 kilohertz. This is the switching frequency. We have current ratings 500 amp, 550 amp and 480 amp. These are different currents we have, and operating temperature also they are different. So what are the types of VFD model available as in the market? So these are the some of the models of one of the company ACS 800. The maximum rating generally up to 5600 kilowatts. It will run at 690 volts. Similarly, we have ACS 850. It is for the smaller capacity 0.37 to 560 kilowatt. So 0.5 to 700 HP we will say. Even for synchronous and permanent magnet motors also we can use this. And ACS 550, this is for smaller capacity we will use for up to 500 HP motors. The first two are used for constant torque applications and 550 used for variable torque applications. So thank you friends. Thanks for watching. If you have any questions or comments or anything, then please comment in comment section. I'm ready to make things clear. Thank you. Thanks for watching. We will meet in next video. Subscribe to this channel so that whenever I'm uploading videos, you will get notification. Bye. We will meet in next video, guys.